Right. So today basically we'll start week 8, which is apparently the last week of linear algebra. So in week 7, it ended with inner product, right? Inner product and norm.
Yes, sir.
So
Yes, sir.
can someone tell me, anyone just, what is an inner product? Or what is the inner product space?
The set of vectors
Yeah.
it's a function on a vector space,
Mhm.
and it has
On
certain
a vector
criteria.
space, I mean, it's a function from a vector space to R,
From a vector space to R, yeah.
or G cross V to R.
V cross V to R. Same.
So, yeah,
It's a
not from V
function
to
from
R.
so a vector space V cross V to R such that
Mhm.
the inner product of the vector itself has to be greater than or equal to 0. So the vector width itself, and it's only 0 if the vector is the 0 vector. Uh, it is also bilinear and symmetrical.
Right. Yeah. So let me start from recalling this last lecture, basically from the definition of inner product and norm. Then we'll enter to week 8 because they are closely related. So, yeah, I will use this PDF for this. So this is the definition she has said already, right? So this is from a function which is from G cross V to R. So you all know what Cartesian product is. And in my last session, I have explained this, and which has these four properties. So if this function has these four properties, then we call it an inner product. So that's the simple definition which we have. Uh, so if we just check for the first one, is it an inner product? The example, can you see? So this is from R2 cross R2 to R. The function is defined like this. So is it an inner product?
No.
No.
No, sir.
Why?
So the standard inner product has summation the same value. The sigma cannot take two I and j. It has to be either I or j. We cannot have cross terms. Otherwise, we are going to end up with cross terms. If it has to
So
be a standard
what
inner
is
product.
this term actually? Can you tell me what this term is?
X1,
What
X2,
this
X1,
summation is?
Y1
Hmm.
x1, y1
plus
plus
X1,
two.
Y2,
Yeah.
Hmm.
X2, Y1, X2,
Okay.
Y2.
Okay. So which property? So if we want to check the first property, what we should do?
So we
If we
would
want to
take the
check
inner
the
product
first
of x1 comma x2 with x1 comma x2 to check the
right,
positive definite.
right. So if I put it down, I will write both x1, x2 like this. What I will get?
X1 plus X
X
and
X1 square
x1
plus
square plus
x1,
X1,
x1
X2,
x2
x2,
Hmm.
x2,
plus
x1,
x2 x1 plus x2 square.
X2
x2
square,
square.
So what this is?
X1 plus X2 whole
x1 plus
square.
x2 whole square.
Correct. Is it clear to everyone till this
Yes.
time?
Yes, sir.
Yes, sir.
Okay.
And why
So
I
is
know
it
for that.
greater than zero always?
No,
No.
sir.
No, sir.
No.
Plus greater
If we
than
take
0,
1
sir.
comma min
One.
if we take a coordinate 1 comma minus 1, then it's becoming 0, so it's violating that if and only if condition.
So my first question was, is it always greater than equal to zero? So that property is
Yes,
good, right?
Yes,
It is
that is
always
yes,
greater than
that
equal
is
to zero.
That is true.
Yes,
Yeah.
sir, that is
But
fulfilled.
yeah, but what is the problem when it is
x1 is minus
yes.
x2, then it will be 0.
correct? So it is basically x1 equal to minus x2. So if I choose any such vector, as you have already said, 1 comma minus 1, then also the inner product is becoming 0, right? Which should not be, because it is saying that it is 0 if and only v is 0. So only possibility should be 0 comma 0, right? But here there are many other examples for that. Okay? So it is not an inner product. Is it clear to everyone?
Yes, sir.
Yes.
Yes, sir.
Okay. Anyone has any doubt in this? I am just recalling the last portion of week 7. So if we see this next question, suppose we have two inner product, right? Inner product means the function from V cross V to R. So these two are two functions with subscript 1 and 2. If I add these two inner product, add these two function, then will that be an inner product? So that is the
I
question.
think so.
Yes.
Yeah.
Yes.
Okay, first of all, what do we mean by adding two inner product?
They're both functions from V cross V to R, so it would
Okay.
just be adding the actual values here.
Exactly. So it is from V cross V to R. This is the first function, and this one is the second function. So what this addition actually means? It will take a value from V cross V, and it will take to R, and this is, I mean, suppose I have this V1, V2, then this is V1, V2 of 1 plus V1, V2 of 2. Right? This is what
Yeah.
this function is. Now the point is this an inner product or not?
It will be, sir, because the other two are inner products itself. So they satisfy all the conditions. And then when you add them, then it will end up
Right.
satisfying.
Okay. Is it clear to everyone, or
Yes, sir.
Yes, sir.
what about the first property? How would it satisfy?
Sir, because you're adding two positive numbers, they'll always be greater than or equal to 0.
So that is fine. If
Yeah.
I take VV, so if I write this is greater than equal to 0, and this is also greater than equal to 0, right? Because they are inner product. So the sum is all obviously greater than equal to 0. Now when this is 0,
When V is 0.
When V is 0.
so if this is 0 means what? These two are positive, so only possibility is both of them are 0, right? So VV1 is 0 and which is same as VV2. So V should be 0 because they are inner product by themselves. Right? So first property is satisfied. Now if you check for the other three property, they will also be satisfied because they are just sum of these. Right? The distributive property of addition that will come along, then the scalar multiple that will also hold, and if we the commutative property, the symmetric property that will also hold. Right? Anyone has any doubt in this?
No, sir.
No, sir.
Okay. If anyone has any doubt till this point, you can ask. Okay. Anyone in this call?
Sir, I
has
have a
any-
doubt in previous question.
Yeah. Okay. Tell me what are
Yes, sir. Suppose we have x1 plus x2 the whole square, and we have some additional terms like minus x1 or minus 2x1, something like that. So on that case, how I tell if and only if it is equal to 0 vector?
No, in that case, first of all, is it always greater than 0? That is the first question you should ask.
Yeah, that is I understand. So suppose in case if we have append that term minus 2x1 here,
Huh.
so
So let's say
x1,
you have got this
yeah,
2x1.
like this.
Huh. So
So
can
in
you
this case,
choose
I can-
x1, x2 such that this is less than 0? Can we choose some x1, x2 like that?
yeah, there is a possible to choose like that.
Then then the first position is not satisfied, right?
Yes.
So it will not be an inner product.
Yeah. So could you solve with this equation like this x1 plus x2 the whole square equal to 0? Like if we solve that type, then 2x square root of 2x1.
No, why we need to solve the second one? The first condition itself is not satisfying. No?
Okay, sir.
So
If it is satisfied, then we need to
then
equal.
move to the second one. That's how it is designed, right? First of all, it should be greater than 0. Then when it is 0, only when V is 0.
Okay.
The first condition itself is not satisfied, then there is no point in going the second one,
Okay, sir.
right?
Yeah.
Yeah.
Thank you, sir.
Yeah, okay, fine. Any more doubt in these two problems? So this one is really important. Basically, if we add two inner product, we will get another inner product. So this has some uses. application which you will see. Now we gradually are entering to week 8 concept. So this question, I think some of you have seen. It is saying that if u v is 0, the inner product of u and v is 0 for all u of the vector space. Right? You choose any vector u from the vector space and take the inner product with a fixed vector v in that vector space itself, and it is giving you 0. Then the v should be 0. V must be 0. Is it true or false?
True.
True.
So it's not true if v is orthogonal to any vector of u, then
No.
the inner product would be
Understand
0
what it
as
is saying.
well.
No, understand later what we are saying. I have a vector space V, right? I have fixed a vector. This vector is fixed. Okay. Now this U is varying over throughout V.
Okay. So I just
Something.
misinterpreted that. Okay. Now I got it. Okay.
Okay. Now this is saying 0. This is 0. Choose any vector U. Then can we conclude that V is 0? Or if not, give me a counter example.
V is 0 only, sir, in this case. Because for all u and v.
Then prove it. Why V is 0?
So if you just take like, if you take the standard inner product.
No,
Sir,
you cannot
by
do-
using
cannot take standard because this
Okay.
is
sir,
really
by using second property,
Yeah.
I can conclude that.
okay. Second property means what?
Sir, let you can take u as a x1 plus x2 and v as a 0. Then it ultimately gives you 0.
X1 plus x2. I mean,
Equal
two
to-
different vector you are saying.
Yes.
So take u1 and u2, right? That is what you are saying.
Yes, sir.
And take the addition of this,
Yes, sir.
then this v, then this is 0. Then
Sir, if v is 0, then we can get this as a 0.
no, you are saying if v is 0, then this is 0. My question is if this is 0, then prove v is 0. You are doing the opposite one, which is obvious.
Sorry, sir.
Yeah. You understand what mistake are you doing?
Yes, sir.
You are choosing this as 0 and taking inner product with any 0, that will be 0. That is fine.
Yes, sir.
But I am asking for the opposite one.
Sir,
Yeah.
v is also in v, right?
Exactly.
So the it has to be 0 vector for it to be 0 in the.
Correct. So this u is varying over all v, right? You can take any value, any vector from v. So I can choose u as v. So this is also 0, right? Because u is coming from all v. This is for all vector from v, right? So v is also a vector of v. So I can take u as v, and it is giving me 0 by the condition. Now, when it is 0, the definition of inner product is saying this is 0 if and only if v is 0.
V is 0.
Clear? The proof is very simple, but you have to just think what we should choose. Is it clear to everyone?
Yes, sir.
Yes, sir.
Yes, sir.
Yeah. So
This is a sub part of a question.
what?
This is a sub part of a question. Like if we are given a small v, we have to assume that the capital V is the set in from which we are taking it.
No, not sub part of a question. Basically, this is saying if I fix a vector, right, and I choose any vector from my vector space, and for all the vectors I am getting 0 as inner product, then the vector I have chosen, that must be 0. This cannot be a non-zero vector. That is what it is saying. Clear?
Yes, sir.
Okay. Anyone has any doubt in this?
No, sir.
No, sir.
Okay, great. So this is one small example. This is another one which I think you have done. Is it a vector space? So here my vector space is M2 cross 2R. So basically set of all matrices A, B, C, D, where A, B, C, D are real. This is M2 cross 2R. This is my V. So I have to choose two matrices, A and B. And how the inner product is defined? I should take the multiple AB and take the trace of it. Is it a vector space?
No.
A vector
It's not an inner
space?
product,
It's
actually.
not an inner
It's not an
product,
inner
but it is a
product.
vector
Right.
space.
Yeah, vector.
Vector
Sorry,
space,
my
but not
question
inner product.
is it an inner product? Huh? Vector space?
It's not an inner
It's
product.
not an
It's
inner.
not an
Not-
inner
not.
product.
Why?
Positive definition is not.
Yeah.
So how we should show that?
We take A, B, C, D, and then
So two artery matrices and do the same thing.
Okay, so let's take that. Okay. For one example, let's do that. What is this first element?
AE
AE
plus
plus
B
BG.
plus BG.
AF.
I don't need
A-
this one. I don't need
Yeah.
this one. I need only this one. What is should be?
E.
CF
AF
plus
plus
AF
AH.
plus D.
This is. So what is trace of it?
Some of
AE
the
plus
diagrams.
BG plus
AE
plus
AF
BG
plus
plus
AH.
plus
CF
DH.
plus C.
Right. Now, so this is my A. This is my B. Right. So inner product of AB is basically this formula. That is what I have got. I should not call it inner product. This function is giving me this one. Now, if I take both as the same matrix, what I will get? So EFGH is also ABCD. Yeah. So what
So
I am
A
getting?
square plus BC
A square
plus
Yeah.
BC
Hmm.
plus BC plus
DC
D square.
D square.
plus D square.
So what is it?
A square plus D square plus 2DC.
DC.
Now, is it always greater than 0?
No.
No, something.
Can you give me a counter example?
Sir, 1 minus 2, 2, 1, if you take row wise,
लॉक करो
then your
Minus 2.
धीरे
2
धीरे
and
जाना
1. Then your 2BC is going to be 2 into 4
Right.
minus
So
8.
in this case, if I take these two matrices, same. The inner product will be 1 square plus 1 square minus 2 into 2 into 2, right? So 2 minus 8, that is 6. Okay. More easier example you could take. You can choose A and D as 0 itself.
Yeah, that
Take
also.
any of the.
Yeah.
So 0, 0 and take this minus 1.
Anything, yeah.
So if I take this thing, this will also give me, so 0 minus 2. So this is negative. Okay, so there are plenty of examples, and this is how you should do this. So this is not an inner product, right?
Yes, sir.
No.
Yes.
Yes, it's not.
Can you give the standard inner? What is the standard inner product for matrix? Do you remember that?
1,
So it's
0,
trace
2.
of AB transpose.
Transpose.
Right. This one. This we did in the earlier live session. So if I define this, this will be an inner product. You can check. Okay.
Sir, this is a standard inner product of matrices.
This is the standard inner product for matrix. Yeah.
Okay, okay, sir.
Okay, fine. So more or less inner product is clear to everyone. Anyone has any doubt in the definition of inner product? How we should check? Anyone has any doubt?
No, sir.
No, sir.
What is, I am not getting response from the others. I am only hearing 2-3 voices.
नो सर नो प्रॉब्लम
No, sir. No,
Okay,
sir.
great. Okay, now let's come to norm. So in the earlier class, I have said that norm is basically coming from the definition of length, right? Length of a vector. That is what we generalized in the definition of norm. So it is basically a mapping a function from V to R, right? Because we take a vector and define its norm, right? How lengthy it is. That is what we are doing. And how it is defined, it should satisfy these three properties. So first one is basically you have seen triangle inequality. Second one is the scalar property, which is coming outside, and third one is positive definitely. Right? So if these three properties satisfy, then we call it a norm. And suppose inside a inner product space, we have some norm, and in that case, this Cauchy square singularity will always satisfy. What does it mean? If we take two vector, if we take the inner product of it, now that is a real number, right? That may not be always greater than 0. So we take mod of it. The mod of it is always less than equal to the product of the norm of those two. That is what this Cauchy square is saying, right? So why this is so important? Why we are actually learning this Cauchy squares? That is the first question that should come to our mind. And is there any relation between this inner product and norm? So anyone wants to say what you think that relation of between inner product and the norm? We have
A
discussed
norm
it
can
earlier.
be a
Yeah.
root of an inner product.
So this is basically saying if we are inside an inner product space, that means we have a vector space which has an inner product. In that case, we can use the inner product to define a norm, right?
It does depend on the definition which is defined, right? I mean, on that inner product space. It could be anything. I mean, the inner product definition could be
inner
anything.
product can be anything. Yeah, inner product can be anything.
So the norm would be, I mean, we can apply the same definition on the norm and we can get the norm of any vector within that inner product space.
Exactly, with respect to that inner product, right? If we change my inner product, the norm will be different. So the norm of a vector is not fixed. That is the first thing you observe from here, right? Because if we change the inner product, then the norm will be different. And even there are some norms which are independent of inner product. I mean, which is not dependent on the inner product. Right? I will show some example. But first of all, from the inner product, how we can define the norm? This is the way. We take the inner product of the vector and take the square root of it. That is how we define a norm. So first of all, is it a norm? I mean, norm. If it is a norm, then it should satisfy these three properties. Correct? So can we check these three properties using this definition? Do you understand, right? This is basically norm of x is root over xx. That is what this definition is saying. So what first property what we should check?
So the positive definite would be the handy to check first, I guess.
But let's start from the first one. Right? How the chronology is there, let's go by that. So how the first one we should check? Any idea how we should approach this? If I have to check these three property for this norm, how we should start?
So you just like plug in the inner product, like the inside of norm of x in which you just put the.
So basically take two vector, right? X and
So
y.
we can take two
X
vectors.
and y is
Right.
inner product.
And as it is a square root, so let's remove the square root. So I will take square of that.
Yeah.
So this is xx. This is y. And what about x plus y square?
Inner product of x.
X plus y comma x plus y.
Now, using the property of inner product, can we break it down? This one.
Yeah.
How?
So x plus y with x, x plus y with y.
So basically the property was saying the first one I can break it down like this. Right? This is what we can do by this property. You remember? This one, the second property we are using. Right?
Yes, sir.
Is it clear to everyone?
Yes, sir.
Yes, sir.
Okay. Now I want to break the second one too, but second one there is no axiom. What I should do?
So
The
the
symmetry property,
symmetry.
we can just switch it.
It is symmetry. I can rewrite it like this. Now I can break the first one again. Right? Understood?
Yeah.
What is this one? We have already seen.
Norm of x
Norm
square.
Norm
of
of
x
x
square.
Okay. And these two are equal, right?
Yes.
Yeah.
Yes, sir.
xy and y. So 2, let me write 2xy. And what about this one?
Norm of y.
Norm of
Norm
y
of
square.
y square.
Okay. Now, can we see, is there any way I can apply the Cauchy squares now? Cauchy square is saying inner product of xy, there is a mod, obviously, is less than equal to norm of xy, right? Norm of x into norm of y, right? So, if I want to make it like this, say 2 norm of x, norm of y, plus norm of y square. Now, this is basically, so Cauchy square is saying this is greater than equal to mod of x, right? This is what Cauchy square is. Correct?
Yeah.
This one.
Correct.
Yes.
Yes,
Right,
sir.
just this one. Okay. And there is a 2 on both sides. Well, this is I am saying. So which one? This one is greater or this one? Which one is greater? What sign I should put here? Less than equal or greater than equal? For the
Less,
Cauchy square.
greater than equal.
Greater than.
Greater than equal. So this side I am using norm.
The
Addition.
norm problem.
Norm of
Norm.
x, right?
So
this
yeah,
side.
this would be greater.
So this should be greater than equal. Right. And if I take, so this will be basically norm of x plus norm of y whole square. This type of thing we are coming, right?
Yeah.
So that is what my first property is. Correct? Both of them are positive, so it does not matter. Now we have square on both sides. So what we got eventually, norm of x plus y whole square, and that is what we have got, less than equal to norm x plus norm of y whole square. This is what we got, right? And both
Yes,
of
sir.
them are positive. So what we get, this number is basically less than equal to this number. That is what triangle inequality is. So we can just remove the square. Because both of them are positive, right? They are not. So everything is positive. That is what we are doing. Correct? Understood what we are doing?
Yes, sir.
Yes,
Yes,
So
sir.
this is an application of Cauchy squares, and using the Cauchy squares, basically we can show the triangle inequality when you use the inner product to define a norm. So this is why Cauchy squares is so important. Okay, and I think the next two property you can check by yourself, right? Nothing special. So norm of cx, what this should be?
Cx comma Cx.
CX comma CX.
Then this is c
So
squared.
square
The
x
square
comma x.
is
Comma
equal
x.
So we gotta take
If
the
I
positive
have to
square
change
root.
the outside,
to norm of x.
this should be mod, right? Because it can be taken
It has to be
Yeah.
positive square root. So we gotta take the
Right.
only positive part.
Exactly. And rest is basically square root.
The norm of x.
So this is normal. So this is what the second property is. And third property, again, it is always greater than 0 because x is always greater than 0 and we are taking positive square root. And when it is 0, when the term inside it is 0 and x inner product is 0, if and only if x is 0. Right? That is the definition of inner product. We have used the definition. So only to use the first one, only to prove the first one, we need to use the Cauchy square. Rest are from the definition. And what eventually it is giving us, that if we have any inner product, then we can define a norm out of it. Is it clear to everyone?
Yes, sir.
You don't need the proof, but at least you have understood how it is connected, right? You don't, whatever proof I
Yes,
have
sir.
done, you don't need that, but at least you have
Excuse
understood.
me, sir. Have
Yeah.
you completed this orthogonality and linear
I have
independence?
not reached there yet. I am just revising the norm and inner product in
Okay, week 8. I guess.
7.
No, week 7.
week
Yeah.
7. Yeah, week 7
Okay,
last
okay.
chapter I am just revising because we will
Oh.
need that for orthogonality, right?
Yes, we will need that. So norm is just the length, right?
Norm is just a length, but here the concept of length is little bit different, right?
dot
we are coming
product,
via-
summation of dot product, no?
Not always, right? Dot product is a special type of inner product. Now, if we change the definition of inner product, we will get different norm,
Okay.
correct?
Mm-hmm.
So that is what I will come next. So before going to this problem, So what we have seen, if I have vector, then I can define a norm like this, right? So just now he has said that it is basically the dot product coming from dot product. So let's see if in R2, let's do it in R2. It is in R2. And I am defining this V1, V2. So V1 is X1, Y1, V2 is X2, Y2. Right? If I want to define it as dot product, V1 dot V2, what is this? This is basically X1, X2 plus
Plus
Y1.
Y1,
Y1, Y2.
Then what the norm will be? If I define it like this, norm of V is XY.
So it would be
Yeah.
root of x square plus y
Yes,
square.
Correct. So this is the usual norm. No, this is the length, actual length, Euclidean norm. This is called Euclidean. And this is the length we have studied in class 11.
Sir, sorry, but I don't get why this x square plus y square we got. Since we are calculating the length, so how
Have you
from?
joined just now?
Yes, sir.
So what if we take xy with the dot product? What I will get?
Okay, x square plus okay, x square.
And that's how
Okay.
this norm is defined.
Okay,
Right?
okay, sir. Yeah, actually, I joined just now. I have to see previous things.
Okay. Fine. So this part you have understood, right?
Yes, sir.
Okay. Now the point is, if I change the inner product, can you give any other inner product in R2 other than dot product? Any other?
So if you have x1, y1, x2, y2, then you can have x1, x2 minus x1, y, sorry, x2, x1, sorry.
No,
X,
I'm getting
write it
confused.
down and then
One second.
x1, x2.
If
So it's so
X1,
v1, v2 minus v something like that. I mean minus the second term, then minus the first term, something
Minus,
like that.
yeah.
So
One
x1,
minute.
x2. So x1, x2
X1, X2.
minus x1, x1, y2
minus
minus,
x2
Minus
y1
x2, y1,
X2, Y1.
so something like this.
Plus
and then
4
plus
times
y1,
y1 y2
y2.
Y2.
yeah,
4x. You can take
4.
2 as well, or 4.
2 times
Two
is
times.
fine.
Let's suppose. Fine. Is it an inner product?
Yes.
Yes.
yes sir it is
Yes, sir, it is.
Okay. Because if we take, so what is the norm coming out of this? If this is an inner product, then if we define the norm in the same way as I have done earlier, this root over of inner product V. So, and V is basically your XY. Then what is the norm coming out of it?
x square
square,
square root of x square minus
minus xy,
2xy
minus
and
2xy plus 4y square.
plus 4y square.
And can we simplify it little bit?
Yeah. So you'll get
Yeah.
x
Yes, sir. X
minus
square.
y whole
X
square.
X minus y whole
minus
square
y.
plus 3.
Plus
Plus
3y
3y.
square.
Correct. So you can see that this norm, this length, now this is also a length, right? This way I can define my length, right? Because this is a norm. Now this norm is defined from the Euclidean, right? It
Yes,
will
sir.
also satisfy all the property of norm because we have checked, because whatever way I can define, I mean, if this is the definition, then it will satisfy the definition of norm. We have already checked in the earlier example, right? This is a norm we have checked. So whatever inner product I will take, this will be a norm. So this is our new norm with respect to defined inner product. So if my inner product changes, the norm will change. Right? So the length of a vector, which till now we had an idea, that is root over x square plus y square, the Euclidean norm. That is a specific norm. That is one example of norm. But there can be defined norm in the same vector space. It only depends on how we are defining our inner product or how we are defining our norm. Is it clear?
Yes, sir.
Yes,
Sir,
sir.
I have one doubt.
Yeah.
Sir, constructing this norm like x1, x2 minus x1, y2, this one. So how they construct this for sure it is an inner product? Is there any trick or any identification for this?
Yeah, there is a trick, but if I tell you, it will be little bit difficult for you. Basically, okay. So let me give you one idea how you should define it. So there are x1, x2, y1, y2, right? And
Yes.
4 terms are basically there.
Yeah.
The combination of these x1, x2, x1, y2, x2, y1,
And
y1, y2. So basically, I can write the coefficient of this as a matrix, right? Suppose the coefficient of x1, x2 is 1. x1, y2, I write it here. x2, y1, I write here and here, right?
Okay.
Now, this should be a positive definite matrix. What does it mean? It means the eigenvalue of this matrix should be positive. All the eigenvalues, right? If it satisfies that property, then it will be an inner product. So you have not started eigenvalue yet, so it doesn't make any sense. But yeah, there is a way in which we can define this.
Okay.
As many as example we want, we can create like this, right? So this is the process which going behind this.
Okay.
So, sir, other than eigenvalues, is there any other way? Or
No. Actually, this is actually what we are doing. Yeah. You take the thing and write a matrix, right? It will be a square matrix, whatever. So in R3, it will be a 3 cross 3 matrix. And that matrix should be positive definite. That is the property. Whenever that is positive definite, and you understand that term positive definite is basically matching with the positive definite property of the inner product, right? So that's how they are going parallel. So whenever that matrix is positive definite, this will be an inner product. That is the relation.
Okay.
So for simplicity, what you can do, there will be square term which is positive, and sum of 2 square term. That is one easier way to remember, but that may not always be the case. This is one sub case of it. As you can see, this is sum of 2 square terms. It will be like that always.
So what's the point of defining norms on other inner products? And like defining other inner products itself.
Right. So there, one Euclidean norm is basically, this is used in all our calculation in coordinate geometry that we have seen, right?
Yeah.
This usual norm. Now, by changing the norm, the geometry of the plane or geometry of the space which we are working, that is completely changing.
Right. Yeah.
So the concept of distance between 2 points, that is changing. So it will totally change our space, and we may need that type of space for solving some other problems. Right? So this is going very deep, very deep. This is all the inner product you are seeing on Rn, right? There can be inner product on matrices. There can be inner product on some other vector space. There are many other vector spaces too, right? Functional space, if you have heard the names. And their norms are coming with respect to integration. And that will create a new mathematical topic that is called functional analysis. And that has an application in solving partial differential equations. So I will not go there. That is really deep topic, and that is go beyond this, very much beyond this course. That is complete full-fledged mathematics course. Okay. But yeah, there are uses. That is the point. Okay.
Yes, sir.
Okay, great. So this is what we have done. Okay. Now see, this consider a vector in R3 which is defined A1, B1, C1. Which one of these are possible candidate for norm? So first one, it is easy for you that it is a norm, right? Because this is the usual.
Yes, sir. It is actually a norm.
It is usual Euclidean. Now, what is problem for this one, the second one?
It may not be always greater than 0.
Components actually. It's not. It's like that.
So basically, if I take 1, 1, something, anything here, the norm of it will be
1 minus 1.
1 minus 1, that is 0. So it contradicts the property, right?
Yes.
Norm V is 0 if and only V is 0. This property is not satisfying, correct? What about the third one?
So likes that same.
Same
So
thing.
it's the same thing. 1, 1, minus 2.
Similar.
Then it's 0.
Exactly. So for the third one, I can choose 1, 1, minus 2. It will give me 0. What about the fourth one?
0
So it's not
minus 1
positive
minus
definite.
1.
If you have many
It's not
if
positive
you have a
definite because
negative minus
0
one,
minus
it
1.
could be
minus 1 minus 1.
Minus 1
Exactly.
minus 1, I can give 0
Yeah,
again.
exactly. And anyway, if we take
it's not
as you were
0
saying,
actually. It's
You
not
can
0.
even
I
get
mean, if
negative
we take
numbers
0
from this
minus 1
norm.
minus 2, then the max value
Max
would
value
give
will be
0.
0.
Will be
0.
0.
So yeah.
And if you take a minus 1 minus 1 minus 1, your max value
Then
is
it
less
would
than
give
0.
minus 1. So it
exactly,
has to be
that
a
will be
mod
negative.
with everything.
You have to have an absolute value.
Right. Now, the point is, so this
Sir-
one you have understood, right?
Oh.
Similarly for the last one. the same
In
process.
fourth one, even if we have mod, and if we take all 0, 0, oh yeah, then it would be 0.
So that is my next question. If I take this max with mod, so let me write x, y, z then. ABC is there. So x, y, z in R2, R3, and I am defining the norm of x, y, z. The function. Is it a norm?
Yes.
Yes.
Yes, sir.
Yes,
It's
yes.
a norm,
It
sir.
is a norm.
Okay, so first property is satisfied, that is clear, right? Because mod,
Yes,
everything
sir.
is positive, max will be positive. When it is 0,
So when
max
Zero.
it's
By that and
max is 0, so it's a 0
max
value.
0 and everything is positive, so all of them should be 0. Right?
Yeah.
X, Y, and 0. Yeah. And modulus property. So mod basically satisfied angle equivalent. Right? The mod.
Yeah,
We take
it
mod of
satisfies.
these two number, mod of A plus B. That is always mod A plus mod B.
Mod A plus mod B.
So if I use this, I will get the triangle inequality property for this one. What about the scalar property? Is the
That is
scalar
also-
coming out?
Yes, sir.
So that is
That's
that is
also
also satisfied because I mean whatever the max value would be in between x, y, and z. So whatever we multiply, it doesn't change the max value actually. So we can pull out the mod c outside. So it would
Exactly.
be it would be still
And that
satisfied.
is because mod C is basically coming out, right?
yeah.
when
You
I
get
am-
Yes,
mod
sir.
CX, mod CY, and mod
Exactly.
CZ. So you can pull it out. And
So this is basically mod Cx. So this is positive. That is the point. Right? And mod AB is basically mod C. So this is basically mod C into mod X. This is mod C into mod Y. This is mod C into mod Z. Right? And then mod C is positive. That's why I can pull it out. Okay. And similarly, so we have checked all the property. Right? So this is a norm, right? This is another type of norm. Now, there is the proof. I am not giving you the proof. Again, it will require some knowledge of little bit deep mathematics, not. But this is not coming from any inner product. And you can see it, by the way, because there is no inner product. If we take square root of it, suddenly a max will come out. Right? This is just a common
correct.
sense.
Yeah.
Yeah, we are gonna get a definite value for square root for a
Exactly.
particular number.
So if we have an inner product and if the norm is coming from that inner product, that is basically square root of something, but suddenly a max of something cannot come, right? This is clear.
Yes.
So this norm is not coming by the definition we have studied above, right? This definition. So this is one type of norm which is not coming from an inner product. Okay. So even if I have a vector space which don't have any inner product structure, or we don't bother about inner product, still I can define a norm without using the inner product. Okay. So there are two ways. If I have an inner product and if I want to use it, I can use it to define a norm. Square root of inner product of GV, that will give me a norm. Even without using that inner product, I can define in some other way. There are some norms which I can define, which will not take care of the inner product. Is it clear?
Yes, sir.
Yes, sir.
Okay, so this is the sketch which you need to just conceptualize. Okay. Any doubt till this point?
Sir,
Yeah.
Is there name for it, such type of norms?
Is there?
A name for it?
No.
No. Okay.
Yeah. I mean, no name, but this is one type of norm which is not coming from any inner product. That you can say. Okay. So we have understood, right? Norm and inner product and what is the relation between these two. So in lecture, I think you have seen what norm is, what inner product is. That all you have seen in the assignment and all this. But this is one small point which I will suggest you to memorize or take care of, that this norm can be defined using inner product, or also there are some norms which are not coming from any inner product. That is one important concept of inner product space. Okay?
Yes, sir.
Till this step, anybody has any doubt? Because now we are going to start week 8. This is what all background we need. Is it clear to everyone?
Yes.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, great. Okay, now let's come to this. So you all know what definition of orthogonal should be, right? 2 vector. So when I am talking about orthogonal, we already know there is some inner product in our vector space. Some inner product, whatever it can be. I mean, it may not be always the usual dot product, right? There are many types of inner product. So V with some inner product. Now, when we call 2 vector orthogonal to each other, if the inner product is giving me 0, right? This is the definition, the first one, if you can see. 2 non-zero vectors, U and V, from an inner product space are said to be orthogonal if inner product of U and V is 0. Clear?
Yes, sir.
Yes, sir.
Okay. So this is the definition of orthogonal vectors.
So can we also use the 90 degrees between them definition, or this is a
Now you tell me, can we always say 90 degrees?
not necessarily?
90 degrees is only true for the dot product,
Dot product.
Yeah, correct.
right? That is
Yeah.
the issue.
Okay.
Because dot product, you have defined how you have defined dot product, norm of U into norm of V into cos of theta, right?
Yes.
So if you remember your dot product, this is basically norm U, norm V, cos theta.
Cos theta. Yeah.
Now when this dot product is 0, when cos theta is 0,
Cos theta is
because this
0.
norm is
There
positive,
theta. Yeah.
so theta will be 90 degrees. So in
Yes,
that
got it.
case only it is
Okay.
90 degrees. But if we
Okay.
change our inner product, then it
Then
may
this won't hold. Yeah.
So this orthogonal property, it's basically coming from the dot product concept, which
Okay.
is coming from the perpendicular concept, but it may not be always.
So when you generalize it to all vector spaces
Exactly.
and all inner products, it's not necessary. Okay.
Clear?
Yes.
That is why I have recalled all this till this point.
So what does this actually mean orthogonal for the non-dot product?
Orthogonal means just if we take the inner product, I will get the result at 0.
Yeah. That's I understand. If it is a like standard inner product like dot product, then
Then it is
angle
90
between these two vector is 90 degree. But other than this, what that mean actually in geometrically? What is the relation between these two vectors?
That depends on how your inner products is defined. Right? We cannot generalize, give you any generalized geometrical definition. That is the point. That's why a separate orthogonal term is coined here. These two vectors we call orthogonal if the inner product is giving me 0.
Okay.
We cannot talk anything about the angle in between them. That depends on how the inner product is. Okay?
Okay.
Okay, great. Now, so for 2 vector, you know what when they are orthogonal. Now for a set of vectors, right? Suppose I have V1 to Vn, a set of vectors. When I will call this an orthogonal set? If I
When
take
they're
any
mutually
2 vector-
orthogonal.
Exactly. When I take any 2 vector from this set, that will be, and take the inner product, that will give me 0. Right? But
Yes.
not with itself, right?
So for
I
width
mean-
itself, it would give values. I mean,
It will give-
we are
Yeah.
not gonna get 0.
Yeah.
Exactly, because we are talking about only non-zero vector. That's why non-zero vectors are important. Okay?
Yes, sir.
Because only zero vector will give zero with it, right? For inner product. That we have seen in the definition. Clear? So
Yes,
these
sir.
two
Yes, sir.
definition I think is quite easy. Now the third one. You can see this PDF properly, right? Or should I increase it a little more? So the third one is V1 to Vn. I have orthogonal set of vectors. The point is they will be linearly independent. What does it mean? I have an orthogonal set of vectors. That means they are mutually orthogonal. Any two vector will be mutually orthogonal. Then they will be linearly independent. That set is linearly independent. How we can show it?
The linear combination.
We start with the linear combination. So this is what the third statement we are trying to show. So what I have? This is orthogonal set that we know. Now my claim is, so let me write it as claim. I am claiming that this set is linearly independent. So for showing linearly independent, what is the definition we have read? I should write a combination C1, P1, CP1, B2.
Up to Cn Dn is 0.
When it will be linearly independent? If the only solution for this CIs are 0.
Yeah.
Right?
Yeah.
All these CIs are 0. Okay, fine. So let's take inner product of V1 with 0. That is 0, right? Inner product of any vector with 0 is 0.
Yes.
We know that.
Yes.
So
Okay, fine. Now 0 I can replace this 0. I can 0 vector. I can replace with this
The entire term over there.
Combinations. Yeah.
Okay, fine. I can break it down.
Yeah.
C1,
C1,
C1.
C1,
I should have written it in 0
Ulta.
plus then V1 symmetry. But I am not changing because you have understood, right? This has
Yes,
symmetry.
sir.
Yes.
Yeah.
V2, C2.
CV2.
C2, sorry.
Yeah.
Cn Dn.
Vn.
Next, CIs will come
CA.
out.
Yeah, take a common.
Okay, now tell me what is happening.
So apart from the first term, all the term would be 0.
Yes.
Yeah.
Exactly.
Has
right?
to be.
All this term will be 0 because they are orthogonal.
They're orthogonal.
Right? This term is non-zero because this is non-zero vector, right? All these VIs are non-zero. Orthogonal set of non-zero vectors.
So the only possible that constant is 0.
So non-zero means this is positive. This is strictly greater than 0. So only
Yes.
possibility is this C1 should be 0. Is it clear to everyone?
Yes,
Yes,
sir.
sir.
Yes, sir.
Now
So we can show
was
the
there
same
anything-
thing for V2, V3, right?
Exactly.
I mean, same property, so it would be Li.
So there is nothing special with V1, right? I could do that for any VI.
Yes.
V2,
Yes.
V3, Vn.
So
And
CP.
I will for
And
each
that
step
way
I
you'll
will
get
get
every CI is 0.
Yeah.
exactly. So that is the idea. Clear?
Yes, sir.
So I can
Yes.
basically replace this V1 with VI. And in that case, some CI VI will become, so let me write it VI. So just tweak a little bit. And then only at the position where VI matches, other than that everything will be 0. So only CI VI. This will be 0 because all other term will vanish. And this is positive, then CI is 0. And this is true for all. Right? So all the CIs I am getting as 0.
So we are just equating, right? We are just equating left hand
Exactly.
side and right side.
Exactly.
Okay. The point I was not getting why CI is becoming 0. I think that it's not clear in the lecture that the vectors are non-zero vectors.
Now is it clear?
Yes, sir. Now it's clear totally.
Okay, great. So what is the point? Point is whenever I have some orthogonal set of non-zero vector, the set is basically linearly independent. Clear? Is this clear to everyone?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Now tell me one thing. If inside Rn, I have n set of vectors, set of n vectors, v1 to vn, that are orthogonal. Somehow I can find that. What I can say about this v1 to vn? What is
Basis.
So,
It will be a
so this
basis.
v1 to vn would span the entire Rn.
Yeah.
Exactly. It will be a basis,
Basis and a span minimum.
right? Because this will be linearly independent.
Yes.
Yes.
N
And
is
it's
the
a maximum
dimension,
linearly
so it is
independent.
maximal linearly independent. So it is also minimal spanning set, so it is a basis. Clear? So somehow inside R3, if I can find 3 orthogonal set of vectors, I mean 3 vectors which are orthogonal to each other, then that 3 vector will form a basis. And that basis we will call orthogonal basis. That is the next definition. An inner product space, V is an inner product space, a basis which containing mutually orthogonal set of vectors, that will be called orthogonal basis. Because any orthogonal set we know that is linearly independent. And if I have n such thing on a vector space which has dimension n, that must be a basis. That is the point. Clear?
Yes, sir. Sir, but not every basis is orthogonal basis, right? But
Not every basis is orthogonal, obviously.
Okay, okay, sir.
Yeah, I will give example. I will come to that. Any doubt till this point? What I have explained till now? Any questions?
No, sir.
No, sir.
No, sir.
No, sir.
Okay, great. This is easy, right? What we are doing till now?
This is fine. Yeah.
Yeah.
Fine.
Okay. Now,
So sorry to
Yes.
interrupt.
Yeah.
Is this recording is there in the YouTube now? Because it's not live stream. We couldn't see that link and that.
no, actually today somehow YouTube link is not generated, so I am recording this session. I will upload it later.
Okay, okay, so thank you so much.
Okay. Okay. So now there is a point called orthonormal set. What does it mean? So every vector of that set has norm 1. There can be some set of vectors which has norm 1. Now, if I have an orthogonal set of vectors for which every vector has norm 1, then we call it an orthonormal set. So suppose I have, so being orthonormal, first of all, it should be orthogonal. And then all these norms should be 1. If these two conditions hold, then we call it orthonormal set of vectors. Okay. Now, can you tell me, if I give you a orthogonal set of vector, can you generate an orthonormal set from that?
Yes, sir.
Yes, sir.
Yes.
How?
By
So
dividing
by dividing
Dividing
each
the
vector,
norm.
each vector by its norm.
Yeah.
Because that will be again an orthogonal, if you see, because v1, v2, vn are orthogonal. So if I divide it with norm, so take the first vector, okay, and the second vector. Let's see what is happening. What will be the inner product of these two? See,
Zero.
norm is a
Zero.
scalar, right?
Yeah, yeah.
Norm is some
So it
scalar.
Yeah.
is
Take that
1
out.
by norm of v1
Yeah.
into
So we can-
norm of
So I
v1.
will
Pull it
take
out.
this
V2.
norm
Into the inner product of
And the
v1.
inner product of V1.
That's all.
Yeah, we will
Exactly.
minus 0.
And that will
and
be
since
zero.
they are orthogonal, so 0.
Clear? And that will happen for FD, VI, VJ, right? Any two vector. And what about norm of each one now?
Norm will be
Inner
1.
It's now 1, sir.
Yeah, it's
Yeah.
not 1.
I take norm of this. Again, this is a scalar, so it should come outside.
Yeah.
With a mod, now we don't need mod because it is
It's
a
positive.
and this, so this will cancel out that.
You get cancel and you get 1.
Clear?
Yes, sir.
So
Yes,
can you
yes.
again explain this part? This 1 by norm of v1 times v1 means, are we cancelling rest of them to 0 and then we are getting only this single norm that will result to 1, or how we are getting that?
Which one? Which one? This one, this part.
Yes, that part.
Okay. So basically, we are trying to find, suppose this is my new vector W, which is V1 norm of V1. Okay. What is norm of W? That is my question. So this is a scalar, right? Whatever the norm is, this is a scalar. So let me
Yes.
write it C. And this positive, C is positive, right?
Yes.
Okay. So norm of W is basically norm of V1 by C. And this C, 1 by C I can take out.
Yes.
Right? By the property of norm. I am not giving mod because it is anyway positive.
Okay.
Because C was norm of V. Norm is
Yes.
positive. Right? Now replace C. This norm of V1 was C. That is what we have assumed.
Yes. We have assumed that.
So 1 by C into C. That is what.
Okay. Okay.
Right?
I thought we are taking means all the values like we have took here V1,
We
V2.
don't need that. Actually.
Okay.
So basically take any vector. The point is take any vector, divide it with its norm. The new vector what we get, norm of that vector will be 1.
Okay, sir.
That is the thing. Okay?
Yes, sir.
Yeah. So if you remember, I mean, in science, in physics, we have done it in class 11, 12. When we tried to construct the unit vectors along the axis direction. Whatever the vector length is, I just divide with that length so that I get the I, J, K in x-axis, y-axis, z-axis.
Those unit vectors.
That is what we are doing.
Okay.
But in general sense. Okay, clear?
Yes, sir.
Okay, any doubt till this point?
No, sir.
No, sir.
No, sir.
So if I give you a orthogonal set, I can get an orthonormal set out of it. And if I give you an orthogonal basis, I can get an orthonormal basis out of it. Correct?
Yes.
Correct.
Okay.
Yes, sir.
So this was one important thing. Now let's see this problem. Suppose I have a set of vectors, right? V1 to Vn, orthogonal basis. And this is an orthogonal basis, we know. So what does it mean? Any Vi, Vj is 0 and it is a basis, linear independent span the whole vector space. Okay. In an inner product space V, if there exists some V, exists some vector V, for which Vi, if we take inner product with any of the basis vector, that is giving me 0. Then this vector must be 0. So earlier what we did, if you remember, uv 0 for all u in V, then V is 0. This is what we have done.
Yes.
For all V. But here what we are seeing, we don't need actually for all V, all U. We only need the basis vector from the orthogonal set. If that is true for only the basis vector, this Vi's, that is enough to show that V is 0. Yeah. Now this Vi's second coordinate is here. It was first. Now you know it is symmetric, so it doesn't matter. So this V is fixed. This is the fixed one. Earlier this one was the fixed one. Now I was taking inner product with respect to all the vectors in V, and I should get 0. Then only we can say V is 0. Now the point is, we really don't need browse through all the vectors. We only need the basis vectors from an orthogonal set. And if then we get the inner product as 0, then the fixed vector must be 0. That is the point.
Sir, can't you obtain that V as a linear combination of the vectors in the orthogonal
That's
basis?
how we should prove it. I mean, this requires a proof, right?
Yeah, exactly.
Yeah. And how we can prove it? So at least statement is understood by everyone.
Yes, sir.
Yes, sir.
Yes, sir.
Any doubt in the statement? What we are doing?
No.
No, sir.
Now V is any fixed vector, and this V1 to Vn is a basis. So as CS said, CS pointed out correctly. So this I can write as linear combination. Correct? For any basis set of basis vector, I can do that.
Yes, sir.
So here also I should do that. Do the same thing as I was doing the earlier one. Now this Vi is 0. Right? So there is some place where Vi is occurring. So basically what it is saying, V1 is 0, V2 is 0, and so on. Vn is 0, right? All this for all I 1 to n.
Right,
That
right.
is what it is saying. Replace, suppose start with from V1. Let's do that. So I am replacing V by this combination. Correct? So from here I am writing it. I am replacing V with the linear combination.
Yeah.
How I should break it down?
So C1, V1, V1, and so on.
C2, V2, comma, V1.
Correct.
And all of those are going to be 0. Except the V1, V1.
Exactly. Now what I get? So C will come out.
C1. Yeah.
And this be as it is. Now which terms are 0 and why?
So apart from the first term, all of the terms will be 0.
Because it is orthogonal.
Exactly. Because V1 to Vn, that was the orthogonal basis, you remember. So all term will be 0. So only I have left with this one. Now this term is positive, strictly greater than 0, because V1 is a non-zero vector. And why V1 was non-zero? Because it is a basis. So 0 cannot be there. Because if it is, if 0 is there, then it is linearly dependent. It cannot be.
Yeah.
So it is a non-zero vector. So this is greater than 0. So C1 must be 0. Now there was nothing special with V1. I can do same for V2, not all Vn. And when I will do for V2, I will get C2 as 0. When I will do for Vn, I will get Cn as 0. So all these Ci's are 0, right?
Yeah.
So what is the combination? 0 V1, 0 V2 plus 0 Vn. That is 0.
So V is 0.
So we have
So that means V has to be 0.
Exactly. That is what we need to prove, right?
Yes.
So all these Ci's are 0 now. So it is 0. V is 0.
So you can also get it by like the virtue that the orthogonal basis is linearly independent. So like the 0 vector can only be obtained if the all the Ci's are 0.
You are proving that V is
Okay,
0.
yeah. You can't use that to prove the same. Makes sense.
Is it clear to everyone?
Yes, sir.
Yes, sir.
Oh, so it is saying, let me summarize it a little bit again. I have orthogonal basis, right? If I have a vector which is giving me 0 with when I am taking inner product with all these VI's, the basis vector, and I am getting 0, then the vector must be 0. It cannot be any non-zero vector. Any non-zero vector cannot give me 0 with when I am taking inner product with the basis vector for all. That cannot be. That is what it is saying. Right? So any non-zero vector cannot be orthogonal with the orthogonal basis. Right? And now you understand that because that was maximal one. So regarding orthogonality, that basis vector is also maximal. I cannot add any more orthogonal basis to that, orthogonal element to that. I cannot have that. Only 0 vector will be orthogonal to each of them. Clear?
Yes, sir.
Yes, sir.
Yes, sir.
So inside R3, how many orthogonal, mutually orthogonal set I can get? Orthogonal vector I can get?
3.
You cannot get
3.
more than
Infinitely many.
3.
No, 3. No, I am not saying it should be 3. How many? So V1, V2, V3. Mutually orthogonal vector. How many mutually orthogonal vector in a set I can get?
3.
3 maximum.
And how many such set we can get? That is infinite. That
Infinite.
that is different thing. But inside
Yes.
any set, any orthogonal set, there can be maximum 3 vector, not more than that. Yeah.
Because
So
it's
could you repeat that
R3,
again, please?
One by one. What?
Sir, could you repeat that again, please?
That I am doing. Okay. So the point is, suppose I have a vector space, inner product space of dimension n.
Okay.
So I suppose I am giving an orthogonal basis V1, V2, Vn. This is orthogonal basis, right?
Okay.
I cannot have any non-zero vector which is orthogonal to each of them. I cannot have that. This is the maximal one. Right? So inside R3, what is the length of maximal orthogonal set?
3.
It is 3. So it is exactly equal to the dimension.
Yeah, it's exactly
Yeah,
equal to
that is what this theorem is doing. Clear?
yes, sir.
Sir, I have a small doubt here.
Yeah.
Here,
go ahead.
you said that there can't be any means vector which is non-zero inside that particular
Mhm.
this, and dimension is okay. I totally understand that. But here it says v1, v2 up to vn, and there can't be v belonging to v such that v comma vi is equal to 0. So here vi represents that particular vector, or v represents that particular vector.
You tell me.
I think vi, sir.
No, I is varying over 1 to n.
Yes, so any possible means any vector we can take, right? And v is just a linear combination of that particular vi.
Vi is basically coming from this set of vectors, this basis vector.
Yes, okay. But
Yeah.
using that set, we can create a linear combination which will represent v, as we have done in this particular.
Why can we can do that? Can you tell me?
Sir, we have done here because it's v is just a linear combination. V is
Why?
just
Why
represent,
V is linear combination of this Vi?
because v comes from the set v. That means that v is equal to v1, v2, vn
Why
and some
is
c.
equal to the linear combination of Vi's? Why Vi has this property?
Sir, it's orthogonal, right?
Its basis.
It's basis, orthogonal basis. That's why we can do that.
Only basis is enough to write this, right?
Okay, so it doesn't matter if it's orthogonal.
Right. That was the definition of basis, right?
Yes,
Any
sir.
vector can be written as a linear combination of the basis vector.
Yes.
Correct?
Yes.
That's why we have written that. Then
Okay. So means here this that's why vi will be that particular vector which can't be 0 inside.
Vi is a part of basis, so it anyway can be 0, right?
Okay.
Because
And-
can a basis vector have 0?
Span of a basis vector.
No, not span of a basis.
Can
I
have.
am saying inside a basis, can we have 0 vector?
No, sir.
No. Why?
Because that will become dependent.
Exactly. So any Vi cannot be 0 anyway. It cannot be 0 because it is part of basis vector.
Okay.
Now what we are doing, we are taking a V, particular V, which is giving me 0 with any Vi's when we take the inner
Yes.
product.
Yes.
My point is that V must be 0. It cannot be any other non-zero.
Okay.
That is
So
what
we are just proving that.
Exactly.
Got it.
So there is no non-zero vector which is orthogonal to each of these Vi. We cannot have that.
Okay.
Clear?
Yes.
Is it clear to everyone? Anyone has any doubt?
Clear, sir.
Okay. This is really important. Okay. This theorem. So next what we can get. So there is another small theorem which is saying, suppose we have orthogonal basis with an inner product within an inner product space. Now any vector V can be written as this combination. So basically, why we are doing orthogonal? I mean, what is the need of orthogonal basis? We had a basis till now, right? Suppose this is, so let me call it W1 to W1. Just basis, not orthogonal. Right? Take any vector V. This is basis of V, the same vector space. So this V can be written down as C1 W1,
Yeah, linear
C2 W2,
combination.
and Cn Wn, right? This we can do. This is basis, just basis, not orthogonal. Now the point is how we found these CIs. So inside Rn we will get a set of equation, set of linear equation, system of linear equation, and then solve it using Gauss elimination. Then we could find these CIs, right?
Yes,
That
yes.
was the process. Right? That is the tedious process. Now, the advantage of taking orthogonal basis is these CIs are quite clear here. These CIs must be like this. That is the point. That's why orthogonal basis is so important and so easy to use. Okay. So here what it is doing. So if I can write this V as a linear combination of this C1, C2, V2, then we don't need to go to system of linear equation and then solving it. If we prove this theorem, it is saying that This, what is C1? C1 is basically the inner product of V with V1. What is C2? C2 is basically inner product of V with
V2.
So it is becoming, our life is becoming easier. How we can find this scalar? This is the scalar. These are the scalars. CIs. Is it clear? If we prove this theorem. Okay?
Yes, sir.
Is it clear to everyone? Why? What is the need of orthogonal basis? I mean, how powerful orthogonal basis is?
Yeah.
Is it clear to everyone?
Yes, sir.
Yes.
Yes,
So
sir.
basically, it will help us to find the scalars. When I am getting a vector, I am taking a vector inside my vector space, and I want to write it as a linear combination. Earlier, what I had to do, I had to go via Gauss elimination. Right? That is a tedious process. But if I am inside an inner product space, I can easily take an orthogonal basis and write V as linear combination, and I know what CIs are. I don't have to calculate so much. If I know the inner product space, inner product, I can easily calculate CIs. Just take inner product of G with VI. That will give me CI. Clear? So
Yes,
how
sir.
we can do it? Again, the same way, right? Take V as any linear combination of V and then I have to find what these CIs are, right? So what I will do, I will take VV1. Let's see what it is. So VV1 is basically V is a linear combination like this. So same line of proof.
Yeah.
Again break it down. So I am writing it down directly now.
V1, V1.
So okay, let me write C2 also. And so on. Okay. What I should write?
Sir, that one.
V2, V1.
Yeah,
I have
V2,
missed
V1 and
V2, right?
V1.
V2, V1.
Last term is also
Last term is also
V
Vn, VA.
V1.
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 The N comma
Vn,
Comma V1.
same thing only. It
same
is.
thing.
Yeah.
Right. Okay. Now what I will get? All these terms are 0, right? Because they are orthogonal. So only this term is remaining. Right? I have done some mistake here. Can you tell me what mistake I have done? So what I get here? V1 is C V1 V1.
V1,
C1 V1 V1. So what is my C1? C1 is coming as V1 by norm of V1, right? Norm of V1 square.
Yes.
Correct? Okay. Now, but it should I have written down like this. I have not mentioned.
So norm of V1 square, is it?
So it has to be orthonormal then. If the below part
Yes,
has
sir,
to
it
be
should
1.
be orthonormal.
Orthonormal
Exactly.
symbol is 1.
Exactly. So if I start with the orthonormal basis instead of orthogonal, then what I have written is completely correct. Otherwise, what I get? Otherwise, I will get a norm below for everyone. Yeah.
Yeah.
So if I have started with, so let me summarize it. If I have started with orthogonal, and you understand that this is norm. Why? Because the norm we have defined earlier, the usual norm with respect to this, that was this, right? You remember?
Yes.
Using the inner product, I can define a norm. That norm I am talking about. So if I take square, this is basically VB. So I have used that one here. This V1 is basically square of V1, norm of V1. So if I take orthogonal, then the combination is actually GV1 norm of V1 square, V1, VV2 norm of V2 square, V2, and so on. VN norm of Vn square, Vn, and if it is orthonormal, then
The denominator would be 1.
You know the norms
all the
are
denominator will be 1. Exactly. That is what I have written on. Clear?
Yes, sir.
Yes,
So
sir.
can you explain again from the C1 is equal to V comma B1 by norm of
So till this line, have you understood?
Yes,
line?
sir.
Okay. Now earlier you remember that I have defined this norm. Whenever
Yes,
I have
sir.
inner product, I can define a norm out of it. Right?
Yes.
If I am talking about that norm, which is coming from the inner product, so if I take square on both sides, what is
Okay.
inner product of VV? That is norm of V
Norm
square.
of V1 square. Okay.
Now here it is. It should be norm of V1 square. Now what is V1 is? If I
Because
take
we are
this,
taking that square, means both sides.
because otherwise norm is basically square root of it.
Yes.
So we have the inner product. So it is basically square of the norm. Correct? That is what I have done. So this is basically C into norm V1 square. And I am taking norm on the other side. It should come
Okay,
as
sir.
C, right? Clear?
Okay, so we are just shifting it. Okay, I understand. After that,
So now if we have only orthogonal set of vector, now this is C1. Now that same process I can do for C2, C3, Cn, right?
yes, sir. Yes, sir.
Take V with V2. I will get something C2 into norm of V2 square. Correct?
Yes, sir.
So all these Ci's I can replace with this quantity.
Okay.
Right? So whenever I have orthogonal vector, orthogonal basis, so I can write a linear combination and I know what my scalars are.
Okay,
This is
so
my
that is just a scalar. Then C times V1 plus C times V2.
and
It's
we
like
know
that.
what CIs are. We don't have to go to Gauss elimination. We just
Yes.
know
Yes.
what that is. The inner product divided by the norm, the square of the
Okay.
norm. And now if I have orthonormal basis, orthonormal means the norms are 1.
Okay.
Right?
Basically, the length of each inner product is.
Don't call it length.
Okay.
Norm is 1.
Okay, sir.
Can we agree on that? Let's call it norm. Not length.
Okay, sir.
Because length only create a visualization that it is Euclidean.
Okay, sir.
Okay. So the norm is 1. Now when the norm is 1, the denominator will be always 1.
Okay. Yes.
So we
okay.
only left with this. This CIs would be clear.
Yes, sir. So that we wanted to prove.
Yeah.
Okay.
So whenever I have orthonormal basis, I can write any vector as a linear combination where my coefficient, the scalars, are basically V with inner product Vi. That is my Ci.
Okay, sir.
Yeah, that is what we will try. Right? Clear?
Sir, I have a small question also.
Yeah.
Means I am just starting all over from week 5, doing all the practice, activity, and assignment. So if I have any doubt, I should post it in the Discourse, or is there any session where I can go and ask, like we have in Python?
Okay. So there is one session going on, but that particular I am focusing on those who have got little less marks in quiz 1.
Okay.
So that is little bit a slow session where I am taking few problems and trying to solve it explicitly.
Okay. So I
Because
haven't
they are
got
little
any
bit-
mail like that.
How much marks have you got? Can I know?
Means basically I got less than 40%. That's true.
But then you should have got a mail. You should have got a mail. You should have got a mail. I have sent mail to everyone.
Okay, I have to check then. Maybe
Please check that.
Yeah, sure.
And if you don't got a mail, please write to me once.
Okay.
With your mail ID, then I will send. I will add you in that.
Sorry, on Discord I have to write.
No, write a mail directly to me.
Okay.
Because I am taking that session, so I will get a
What is your mail ID, sir?
Sir, like if you want to just join that session for revision sake, like if you just want to say, like if you're discussing questions in depth, right?
But,
We also joining. I got 60 marks, but still, if I.
But that
60
maybe
marks
that
not
session will be a little bit slow for you, no? Because I am going really slow in that session.
The option of just seeing what is going on in that session is still good enough, right? We can just be in observation mode. If something is useful, you can listen.
Yes.
Okay, first let me take 2-3 sessions, then I will open it for everyone. Okay, is that
Can you
fine?
please write your email ID, sir? Because I didn't got any email.
Okay. Sir.
You must have got, but still I am writing. That should be in, huh? In has not.
Sir, one more thing. Can you please upload today's session by today night?
I will upload it.
Okay, sir.
Today
Because
night
sir, I
I
have
cannot
to.
guarantee because this recording has to be processed.
Okay,
I
okay.
can
sir.
upload the PDF just after the session, but video it will come little bit later, maybe tomorrow morning.
Okay, that is fine. Tomorrow morning is also fine. No issue.
Yeah, so this is my mail ID. So the point is, I have created a small group who have got less than 40. Okay. Basically, those who need little bit more slow session to get the quiz to topic. So I am doing a session with them. I have sent mail to everyone who got less than 40, but got reply from few people.
What is the timing for that session?
The last session I have taken on Tuesday at 8.
Night.
At 8. Night. Then next session I have not decided yet, but I will take. Okay, but that will be in night. That will be in night.
I think that it's because I was having statistics and I was focusing there too much. So.
Oh, okay.
But no ways, I will join.
Yeah.
Oh. Same here. I have maths 2, stats 2, and Python. So devoting time is a
yeah, devoting time is.
Okay. Anyway, if you need any type of help regarding this concept, just write to me. I will try to.
Sure, sir.
Anyway, after week 8, we will do some revision session for all. That is already there.
Much appreciated.
Yes, sir.
So till now, what you have seen is clear to everyone?
Yes.
Yes, sir.
Yes, sir.
Okay, great. So before that, yeah.
Before going to this, I have a doubt in activity. So like it's the determinant of a matrix formed by 3 orthonormal vectors. That is plus or minus 1. I understand because I am just getting some random orthogonal basis and putting the matrix and checking them. But is there any standard proof for that one?
Can you say it again? What? Which one are you talking about?
Sir, activity question 4, 8.24. Yeah, this one. So actually I taking that orthonormal basis and forming that matrix and finding the determinant that is plus or minus equal to 1, that is fine. But is there any way to find the standard proof for this one? Because it is true for everyone, right? Anything, right?
Yeah, this is true for anything. Okay.
So you can go by linear independence, right?
That is there. Yeah, can you tell how you are approaching it?
Also, for any matrix that is formed by orthonormal vectors is orthogonal matrix, we call it. And it has this property of A square equal to I. That is, the square of orthogonal matrix always equals an identity matrix.
Exactly. That is what we need.
So the determinant of determinant of A square is nothing but det A whole square, right?
Exactly.
So det A whole square will be 1. So det A can be plus or minus 1.
Exactly. Yeah. True. Have you understood what she is saying?
I understood what
but
she is
little bit not exactly A square, but what actually I should do.
So it's like A transpose equals A inverse, right?
Exactly. That is.
So A transpose dot A is I actually for orthogonal.
So suppose I have 3 vectors, right? Let me call it A1, B1, C1, A2, B2, C2, and A3, B3, C3. And these are column, right?
Yes, sir. The column.
That is not mentioned, just vector. So let me write it in column or row, whatever it is. Okay. So A1, B1, C1, A2, B2, C2, A3, B3, C3, right?
Yes.
And if I write this like this, what is the transpose of it?
A3, B3, and C3.
Now, if you multiply, will be the norm, right? A square plus B square, A1
Yeah,
square plus
that
B1.
is norm.
And the rest will be just 0, the dot product,
Yes.
right? Rest, all these rest are dot product. So this is norm of first column.
Huh.
So let me call it V1, square of that. This is V1 dot V2, V1 V2, the inner product. Right? This is
Yes.
V1 V3, the inner product. This is V2 V1.
2v1 and
And this is
norm
V2 norm.
V2
So you
square.
understood, right? These are 0.
Yeah, that is 0.
And this is orthonormal, so these are 1.
Yeah, this is orthonormal. Oh, okay.
So it
Yes.
is giving me identity matrix. right?
Identity matrix. Correct.
Now what determinant of AAT?
Huh.
Determinant of the
Identity
identity.
of A. Yeah, that is identity.
And A and AT have same determinant.
Yes.
This is 1. So basically this is delta square. This 1. What is delta?
Is 1.
Plus minus 1.
Yeah. Square root plus 1.
Yeah. So this is what?
Yes, sir. Clear, sir. Thank you so much, sir.
Okay, great.
So
Yeah, this
will
is
you
this
take
is a
another
nice
question
So
from 8.1?
if I solve question, then okay, let me see.
If you want, we can take it afterwards also. You can complete.
No, let's see. Let's actually I left with 2 more topics, but anyway we have 1 more session. So
Okay, sir. So the question, it's 8.1, question number, last question, it's 7th one. 7th one and the 6th one.
I will do 1.
Okay. 6th one, sir. This means
This is number of solution of the system.
means I can see that some of them are linear dependent, but why it's 1 only? Why it's not 2?
Actually, it has a unique solution, right?
It has unique solution.
Solution, so it should be 1.
Yeah.
Yeah. It's
So
1.
So means taking the determinant and resulting in
Any
Non-zero.
way you can do that, right?
Hmm?
I mean, you can use any of the method. No issue with that.
Okay.
And I mean, why it is so? The question you may have asked that why it is in this chapter. I mean, in this activity question, because this can be in the first week, right?
Hmm.
But why it is here? Has anybody understood why it is here?
Means how it is connected with this
So you
orthogonal.
can like check it if it you can check if it's an orthogonal set.
Actually, the rows are orthogonal.
Yeah, exactly.
Okay.
Okay, the rows are orthogonal. Now you know. So if the rows are orthogonal, that means in R3, so they are linearly independent. You
Yes,
don't have to
then
go
they
to
are.
Gauss elimination. That is what I was saying.
Hmm.
Why orthogonality is so powerful. So rows are orthogonal mean we don't need. So that is the maximal linear independence. That is the basis because it is in R3.
Okay.
Correct?
So
So
okay.
linear independent basis. So the matrix is invertible. So it has a unique solution.
Okay. And same thing we have to do for question number 7 also.
Huh.
Okay.
Exactly.
I will do it.
But question number 7 has little more.
It's
whatever
A
the
times
same.
A transpose. So
So
means
we'll
I
just do
think
it the same thing.
Hmm.
You know what it is. Just now I have done it.
yes, sir. You have done similar thing.
So why more than one option correct? Because identity matrix has many properties.
Yes.
It is also a diagonal matrix.
Hmm. Okay, sir. So means
Okay.
just check for the orthogonality and means orthogonal is there. So just go about that.
Yeah.
Okay.
Exactly. Okay. Fine. Clear, na? It is. It's clear to everyone, right? That question number 6. The rows are basically orthogonal.
Yes, sir.
Yeah. With respect to usual dot product. Okay. Fine. So where are we? We have seen what orthogonal basis is and what it can do. We can basically simplify the scalars with respect to that. The next thing is basically we will come to projection. What a projection is. Now this is another topic which is basically this is the last portion of linear product. Yeah. So you know what projection is in general. Suppose I am asking you, taking this x-axis or y-axis. Okay. I'm taking a vector, say 4,6. Okay. If I want you to project this vector on x-axis, what will be the projection? Projection on
0,
x-axis.
6. Like you just bring it down basically.
So what it should be?
You make y 0. Sorry,
4,0.
4,0.
4,0.
4,0.
So basically, what we are doing, we are taking a projection on this subspace, right? This x-axis is a subspace, correct?
Yes.
If I want to take position on y-axis, what it should be?
0,6.
0,6.
0,6.
Okay. Now these are two subspaces. Now there are some other subspaces too, right? If I want to take like this one, this is also a subspace, and I can take projection on this also. So, correct?
Yeah.
Yes.
So this is the process which here we will learn, that how we will determine this point, this projection. So this is any arbitrary subspace. So for x-axis and y-axis it is easier because we just make one coordinate 0. But what about some other y equal to mx? This is the line y equal to mx, right? This is also a subspace. Now what will be the projection of 4,6 on that vector space, on that subspace? That is what we will learn, how we will do that. Okay. So the process is very simple. Whenever I have some subspace, right, W, let the subspace call it W. The whole vector space here R2 is my V, and the subspace is W. This is W. Okay, and this is my vector V, 4,6. Now I want to take a projection of 4,6 on the line y equal to mx. Let me be little bit more specific. Let y equal to say 1/2x. Okay, that is passing through. How we will calculate the projection? So first of all, we need a orthonormal basis for W. That is what we need, an orthonormal basis for W. So suppose V1 to Vn is my orthonormal basis. So this is orthonormal.
So why we choose this basis is orthonormal?
I will come to that.
Okay, sir.
We need that also. First of all, can you tell me why we need orthogonal? Actually, I have already said it, why we need orthogonal. So, okay, let me formalize it this way. I am taking projection of V onto that subspace, right? So I will call that vector, new vector, as projection of W, V on W. So this is the vector. Where this vector lie?
In W.
W. So this is vector in W.
So actually that projection is like between the origin and that shadow.
Kind of that.
Okay.
So projection is a vector in W, right? So I can write this vector as a combination of linear combination of the basis vector, right?
Yes.
And just now we have seen that instead of taking any basis vector, if I take orthonormal, I have an advantage.
You can find the C.
I can find the CIs, correct?
Yes.
And that is exactly what we are doing. These are my CIs. That will give you the projection. Yeah.
So theoretically, would this work with a non-orthonormal basis of W?
No, but that will be very much calculative.
Yeah.
Right?
But
But here it is much easier. Just take the orthonormal basis, take the inner product with each of the basis vector of the given vector, and write the linear combination. Because this projection vector is inside W, right? So I should write it as sum of Ci, C1, V1 to Cn, Vn. Now what is this Ci's? We have already calculated. What is this Ci's? These Ci's are nothing but V,
V1, yeah, VVI.
That is my Ci. So if I know this, this combination I know. That is the projection. That's how projection is defined. This is the definition of projection. Okay? Clear? So
Yes,
if I expand it, what I am doing, what I have written earlier. So this is what my position is, and you know how this proof I have done earlier in the earlier example, right? Why these CIs are this, that we have already done the proof, right? In the earlier example, this one, correct?
Yes.
And that's why we have started with an orthonormal basis so that it is more easy to form. Clear?
Yes,
Yes, sir.
Yes, sir.
Okay. Now let's check one thing. So I had 4,6, right? This is my vector V, 4,6. Can you give me an orthonormal basis for this x-axis, this subspace? What is the dimension of this?
1.
1,
1.
1,
So
comma,
if I
0.
have to
1
take
comma
0,
0.
1, comma 0.
This is
Comma 0,
orthonormal,
sir.
right? This is orthonormal. Okay, fine. So this is my basis vector. Basis.
Have you choose this basis 1 comma 0 for which one, x-axis?
Yeah.
Okay.
This is an orthonormal basis, right?
Yeah, so why you didn't choose the standard order basis that is contained? Oh, you have only x-axis, that projection. Okay.
This is one dimensional, right?
Yeah.
So
Yeah.
1,
Yes.
0 is there. Yeah. Okay, fine. So this is one orthonormal basis, right? Now, in the condition, so what is, so this is my V1. Other VIs, there are no other VIs, only V1 is there. So what is V1?
4.
It's a usual dot product.
Because
This is
you
dot
have to
product.
use usual, because the orthonormal basis I choose with respect to the usual one,
Okay.
right? So while choosing the orthonormal basis, you are already fixing your inner product. If you fix some other inner product, then your orthonormal basis will be different. Then you have to use that basis, that inner product to calculate this one. But here, the orthonormal basis I have chosen with respect to the usual inner product, because the length, as you can see, this is the usual
Yes.
Euclidean
Yes.
norm.
Yes. Yeah.
So what is this? 4, right?
4.
4, sir.
Okay, fine. So what is projection of V in the space W? W
4
is
into
x-axis.
1 comma
4
0.
times
4,
4
4,
into
1, 0.
1 comma 0. That is,
Yes.
4,
4
comma 0.
comma 0.
it is matching with the our usual concept, right?
Okay.
That is what we are doing. Clear?
Yes, sir.
Yes, sir.
Should we see the
Yes, sir.
y-axis thing also? You tell me. So V is 4,6. Now quicker. What is y-axis?
0, comma
0,
1.
comma 6.
0,1. This is 1 orthonormal
Hmm.
basis.
Yeah. Inner product is 6.
6.
Inner product is
0 comma
6.
6.
6
So it
times
will be
1, comma
6 into 0
0,
comma
comma
1,
1.
which is 0 comma
So
6.
projection is
6 times 0, comma 1.
so 0.6. It is exactly what we do. Now can you do it for y equal to half x? Y equal to 1 by 2x. So let me write it again. G was 4,6. Our straight line was y equal to 1 by 2x, this space. So let me write it x comma y such that this xy in real. This is
Sir,
the,
how we defined m is equal to half?
I have chosen one.
Okay, you have chosen. Okay, it can be anything.
It can be anything. I have
Okay.
particularly chosen half.
Okay, sir.
Okay? Because the line I have drawn is kindly looking like half.
Okay, sir.
Okay. So can you give me a basis of W? Orthonormal basis.
1 comma half.
Is that orthonormal?
Is that orthonormal?
I don't think so.
No,
1
by root.
So if I
1 by
take
root
this,
5
1
into
by
2
root
comma
2
1.
1.
Yeah. Yeah.
1 by root 5 into 2 comma 1 is orthonormal
2 comma 1.
basis.
Yes.
what? Tell me what? 1 by
1 by root
1 by
5
root 5
1 by root
into
5
into
2
2
comma 1.
comma 1. So it will be 2 by root 5 comma 1 by root 5. Ulta.
1 by root 5 whole into. It's
Yeah,
not
yeah.
1 by root 5
1 by
comma.
root 5 is a scalar and then you have 2 comma 1.
Is it clear now why this one is that?
Weighted
So
system.
So
basically,
we are building that from the condition.
so basically,
dividing it by the
let me
norm.
write it 2y equal to x, right? So take n is equal to 1. So y should be 2, right? I may
Yes,
have
sir.
ended up, sorry, y equal to 1, so x equal to 2. This is a singleton set, so this is linearly independent, right?
Yes, sir.
And this is inside W. So this is the basis of W, right? Any basis. This is a basis of W. At least this part is clear.
Yes, sir.
Yes.
Yes, sir.
Okay, fine. Now it is not normal. This vector is
Yeah.
not normal because the norm is
Yes.
root 5,
Yes.
right?
So we need to
What is the
divide
norm of 2 comma 1?
root 5.
Root 5.
2 square plus 1 square, right? So it is root 5. So if I divide with this norm, then I will get a orthonormal basis.
Yes.
Yes.
So this is 2 comma 1 by root 5. So that is what we have written. Yeah. How we
Yes,
got the
And
basis?
sir, we can even take like 6,2
Anything,
and then do
anything.
the same process.
Yeah. You will get a defined basis. But
Yes.
eventually your result will be same.
Okay.
Okay. That is the thing. Okay.
So you mean
So-
that I will get C as 1 by root 5 only?
No, that is not what I'm saying. I'm saying the projection will be same.
Okay. Yeah.
This will be same. You will get different basis here altogether.
Mhm.
But when you
since-
calculate the projection, still the projection will be same because question is fixed.
Yes,
will come
equation is fixed. That straight line is fixed on which we are projecting.
Yeah, the vector is fixed. So this is V and this is my V1. V1, V1. Now what is V inner product of V with V1?
C
14 upon root 5.
So this is 4 into 2 plus 6. So 14 by root 5, right? Have everyone calculated it?
Yes, sir.
Just 1 by root 5 is
Yes,
scalar,
sir.
so I can take it out. And the dot product 4 into 2, that is 8, plus 6 into 1, that is 6. So 8 plus 6, 14, 14 by root 5. Okay? And what is my V1? 1 by root 5, 2 comma 1. So this is correct? So
Yeah.
14 by 5,
Into 2
comma 1. Clear? So
Yes,
this is basically 28 by 5, comma 14 by 5. Observe that this is on W. This point is on W, right? Y equal to half of X. That is still satisfying. Okay? So this is in W. That what it should be. And if you see 4,6 here, so this point will be 28 by root 5. If you calculate and 14 by that will be our position. Clear?
Yes, sir.
So that
Yes, yes.
14 by root 5 part means you calculated that, right?
Yeah, I mean, do you understand the calculation? I have just.
Actually, no, that's why I'm asking.
So you have understand that this formula we are using, right?
Yes, I understand that.
So the inner product of V and V1, what is that? This is V, this is V1.
Okay, so we are multiplying. Okay, 4 to the 8
1
and
by-
6. So 8 by,
14 by root 5.
yes, 14. Got it.
Right? And then V1. V1 was 1 by root 5 into 2 comma 1.
Okay, so that 1 by root 5 is the V1 that we calculated earlier. That entire V1 we have got there. Okay.
So this is 14 by 5.
Mhm.
That is
Okay.
28 by 5 and 14 by 5.
Okay,
Okay,
sir.
that is my projection. Okay, so we have understood how projection is calculated, right?
Yes, sir.
And it is matching with the idea which we had earlier about the projection. Correct? This portion is clear to everyone?
Sir, that real number value, like 4,6 is projecting this portion. So what the real number actually mean? That is distance from origin from the inner product space, or it is different?
No, if we draw an orthogonal perpendicular line to the surface, not say
Oh,
perpendicular,
this
draw
line.
the
Oh,
normal
okay,
line.
okay, that line. So that's
Where it
perpendicular.
intersect, that is basically the projection, right? That is what.
Yes, yes, sir.
That's why inner product is involved, and that's why orthonormal basis and all these are coming. Because we are basically drawing a normal line from the vector
Okay.
to the subspace we are considering.
Yeah, yeah. So that
Where
perpendicular.
the point of intersection, that is my projection vector.
Okay, so that perpendicular line length is this one.
Ah,
Yes, sir. Okay. Thank you, sir.
that is what you are seeing for x-axis and y-axis, right? The same thing. Yeah. Okay, fine. So this portion projection, at least it is clear, right? And this is what already one of you have pointed out. The projection vector is independent of chosen orthonormal basis. If you choose any other orthonormal basis, eventually the projection vector will be same, right? That is guaranteed. Because anyway, eventually we will calculate the inner product and use the same inner product with respect to that basis. So eventually the vector we will get, that will be same, whatever the basis we consider. Okay.
That means that
So-
basis is we can choose any basis, any orthonormal basis.
Any orthonormal basis. Right?
Okay.
Okay, fine. So now here observe one thing. So I have started with a vector from V, right? And I am getting a vector inside W. So basically this is a map from V to W, no? This projection. I am giving an input from V and I am getting an output as a vector inside W. So my codomain is W, correct?
Yes.
Is it clear to everyone that this
Yes, sir.
projection
Yes, sir.
I can
Yes, sir.
consider as a
Yes, sir.
map from V to W, right? Okay, great. So I can treat this projection as a map from V to W. That part is clear. And W, you remember W was a subspace of V, right? W is sitting inside V. That we know. And so these two are vector spaces, right? V is a vector space, W is a subspace, so it is also a vector space.
Yes.
And this is a map. Now, first question should come to our mind, that is it a linear transformation?
It is.
Why?
Sir, it's a linear combination of those. That's how we look at a linear transformation.
Give me a minute.
Yeah.
1 minute. I'm coming back. Yeah, sorry. Why it is a linear transformation? You can hear me, right?
Yes, sir.
Why it is a linear transformation?
So first, like P of 0 is 0. It will give you
Is
that.
it clear that your projection of 0 is 0? So let me write down again. So what we are doing, let me write it here. Projection of W is the first place. This is VI I equal to 1 to n. Okay? And this VI, V1 to Vn, this is orthonormal basis. Okay. So What is 0? Projection of 0. So 0 vi into vi. And what is that?
0.
0.
0. Because all these inner products are 0, right?
Yes.
Whenever I am taking inner product is 0, all these are 0 and sum of those is 0. Correct. What about projection of two vectors? Sum.
That you can you'll write it as summation of inner product of v1 comma v2 and vi
I
into
should write
vi.
v prime and v double prime because we have already used v1, v2.
Yeah, okay. So v dash dash. That plus that. And then because of the inner product thing, you can split that,
Exactly.
which gives you like t of v dash plus t of v double dash.
Exactly. So for each I, this will split up, right? So I can break it down like this. What is the first one? It is the projection of v prime, and it is the projection of v double prime. Clear?
Yes.
Okay. So and similarly,
For the scalar also you can do it.
Equal to 1 to n CV vi vi. Now C can come outside because this is an inner product. So C can come outside all together as a common element.
C into projection of v.
So this is C into projection. Yeah. So V to W, I have this projection. This is taking projection out of. This is the linear transformation. This is a linear transformation. Is it clear to everyone?
Yes, sir.
Yes, sir.
Okay. Now, whenever I have linear transformation, the first two things which should come out of mind, that what is basically image and what is content, right? Is it on to? Is it 1 to 1? This question should come to our mind, right? Is it on to? So let's start with that question. Is it on to?
So from V to W, then I guess it will be. But if it's
V to W.
and image is W, then it's not.
Why image is W?
Like if image is W and it's from V to V, then W is a subspace of V. So that itself you can say that like it's not the same.
If I am saying the codomain is W itself, is W.
Then it's on to it.
Why? Why all the points of W is becoming an image?
Because you have an orthogonal basis.
So
wait.
Sir, the same basis we can actually span V. Actually, I think the basis of the span of the basis of the subspace, it would be equal to the span of the basis vectors of the whole plane, I guess. The whole vector space.
No, but if W is just a line, then that won't be true. Because the dimension.
W is a subspace. W is a subspace.
That's what.
It can be proper, right? In most of the cases, it is proper subspace. Okay, let me give you a hint. Can you see what are the projection of any element of W? W is inside V, right? Yeah, it is W. So W, if I take any element W from W, it is also inside V, right?
Yes.
So this also I can give it as an input. What the output is in that case?
Sir, will it be the norm of that W square into W?
Itself, sir.
Like that, yeah. Like you'll express it in terms of the basis and all that.
Then what is happening? What will be the projection? Already one of you have said.
Itself, sir. Itself.
Itself. It will be itself. So see, if you remember the example. So when I take 4, 6, and this was my x-axis was my W, I'm taking this 4, 0, right? Now, if I take
Yeah.
any point on x-axis, what will be the projection? The point
Itself
itself,
only,
right?
yeah.
Correct? And it is actually, if we go by the definition, W I can express as a linear combination of this, which is actually this linear combination itself. Correct?
Yes, correct. Yeah.
So what I am saying, W is a linear combination. So what is the linear combination? We know W VI we know this is the linear combination of W, right? V1 to Vn. Correct? I can express W as a linear combination like this because VI's are these are basis element of an orthonormal set of W, right?
Yeah.
Is it clear to everyone what I am saying till now?
Yes, sir.
Yes, sir.
Okay. So what is the projection of W now inside W?
W.
W itself.
It's W itself.
Understood, right? Because I am doing basically this thing itself. This is the definition of projection, and this is actually the linear combination. This same linear combination. So this is W. Okay. So whatever if we choose any element W from W and take the projection on W, that is the element itself, right? So any element of W is already an image, right? Because at least it is the projection of that element itself from V. Correct?
Yes.
So
correct.
image of this projection, this transformation, that is actually W, right?
Right.
Is it clear to everyone?
Yes, sir.
Yes, sir.
Okay, fine. So this is really an important thing. So this is an onto map. This is an onto map. Is it 1-to-1?
No, it's not.
It's not, right?
It's not.
Because you can see this example itself. 4, 0 has a projection 4, 0 and 4, 6
and 4,
or
6
any
also
point
have.
on this line has the
Would
same
have the same
4,
projection.
Yes.
right? So there are many points which is going to the same point, same element, right? So it is not 1-to-1 in general, right? But it is always on. So the projection map which we are talking about is always onto, but may not be 1-to-1. Clear?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, great. So this is what this question number 10 was. The projection is projection and onto linear transformation. The answer is yes. And the image of projection is W, the surface in which we are taking the projection. And the projection is not an 1-to-1 transformation in general. Okay, clear?
Yes.
Any doubt
Yes,
in
sir.
this?
Sir, if
Yeah.
you took the codomain as like the same dimension as the domain, like if you took it from V to V and you just changed it, then would it be 1-1? Like in
What is the
certain
projection
cases?
actually, V to V?
Like you just shift everything basically. Okay.
Each point is the projection of itself. It is
Right,
identity.
right. Yes. Correct. Okay.
Right? It is identity mapping. Then obviously
Yeah,
it is
yeah.
1-to-1. And this is the only case when it is 1-to-1.
Got it.
Right? Otherwise it is not.
Got it.
Okay. Okay, fine. Is till now what we have done is clear to everyone? So this is the last thing I will discuss. I will leave Gram-Schmidt for the next class. Because otherwise again it will be heavy. Already we have done many things, but let's see. Any doubt till this point? Till the projection, how it is defined, why it is linear transformation, why it is onto, but may not be 1-to-1. Is it clear to everyone?
Yes, sir.
Yes, sir.
What about others?
Yes, sir.
I'm getting 2-3 voices.
Yes, sir.
Okay, great.
Yes, sir.
Great. So the last thing which I want to do, that this projection square is basically the projection itself. What is mean? So you remember the composition of function, right? I have function from here to here. And then again if I take, then this is the composition of function f and g. So this is g compose f, I can write, right? Remember that. First I apply f, Then on the image, I am applying G. The result I am get, that is basically G composite. Right? So if I apply to the same thing, F twice, then it is F compose F, and that is what I call F square. Okay? That is not the square of it, just assuming. This is F compose F. So this projection square is basically position of W compose position of W. This is the notation. So what this theorem is saying, if I apply projection twice on a vector space, I am getting back the original projection.
Yes, sir.
If you
Just
think
now,
of
yeah.
this,
Yeah, yeah.
exactly.
Just
So
now,
this
yeah.
is V.
Because W is W only.
V. Here somewhere there is W. Here somewhere there is W. Take again V, and here somewhere there is W. First, I am taking projection. Where everything will come?
W.
Inside W, right? Write it PW. So PW is basically projection. So every vector, whatever that is, the image was all inside W, correct? This is W. This is also W. This is also W. Same thing. I have taken 3 copies. Basically. Now, if I again apply projection on this W, what I will get?
W.
In W.
W itself, right? Now,
So you're gonna get W again.
Yeah, this question is basically identity map. Right? Same element is going to say. Correct? So, what happens all together? What happens PW compose PW? That is basically what PW was doing. Because the next portion is basically identity. Nothing is changing. Right? So
it's like, say, you're projecting the same vector twice. So it's gonna be the same projection every single time. It doesn't matter how many times you're doing that.
Yeah.
Exactly.
And
Once we come to the elements of W, then we are basically repeating the same thing. How many times you are doing. So once the square is same as the original one, if we take PWQ, that is also PW. Right? Because we are applying this law again and again. So if I PW, compose PW, what is that?
PW.
Still PW.
Because this is PW, and then again this is PW. So once the square is same as the original one, then whatever the number you take, PW power, that is still PW. Okay? So if I apply projection twice, that is PW. This is one important thing we should do. Right? So this type of mapping is called idempotent map. You remember something called idempotent matrix. It was in class 11, 12, if you remember. So this is called idempotent map. So projection is idempotent map. Idempotent means if I take the square, I will get the same map back. That is called idempotent. Okay? The term is not important here, but at least you got the idea what actually it is happening. Right?
Yes, sir.
Is it clear to everyone?
Yes, sir.
Yes, sir.
Okay, great. Great. This thing I can post. I will leave it. So then range space, we know what range space of projection it was W, right?
W.
What null space of projection? So this theorem is saying that range space and null space, only 0 vector is in the intersection. So here is V, here is W, here is V, here is W. So if I take this thing, this is the range space W, this is PW. So range of PW, I know this is W. And null space means all those vectors which are going to 0. Right? All those vectors. Now, can any vector which is in W, can it go to 0? Other than 0?
Unless it's 0, it can't because they go to
Unless it's
themselves
0.
Exactly. No other vector which is inside W, if it is not 0, it cannot go to 0, right? Because all the elements of W, PW of W, W is coming from W, that is W itself, right? So if W is non-zero, then it cannot be inside the null space, right? Am I clear?
Yes, sir.
Yes, sir.
If W is non-zero and belongs to W, then W cannot be in null space. It's clear to everyone? Is it clear to everyone?
Yes.
Because for being in
Yes,
null
sir.
space, PW of W should be 0. Now PW of W is actually W, so this W should be 0. So no non-zero vector can go to 0 inside W. But my range space is W, that I know. So what is the intersection of range space and null space?
Only the zero vector.
Only the zero vector.
So other vectors which are going to 0 is outside 0, outside the W. They can go to 0. There can be some vector which is outside W, they can go to 0, but no vector inside W can go to 0. That is what this theorem is saying. Clear?
Yes, sir.
Yes, sir.
Okay, so this is what we need in projection. Okay. Any doubt till this point? So we have done many things again. I will upload this PDF. You should browse through it once again, I think. Right? More or less what we have discussed, is it clear?
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir. So far it is.
Okay, great. So till projection we have discussed the one topic which is remaining, that is Gram-Schmidt, and then orthonormal matrix, that is a small thing which is remaining. But main topic is which is remaining, that is Gram-Schmidt method. So basically when we are talking about projection or any we are talking about any vector space, then we say let's consider an orthonormal basis. But what is the guarantee that there exists an orthonormal basis, right? We have not done anything like this. Why an orthonormal basis should exist in the first place? A basis exists, that we know. But why an orthonormal basis should exist? Basically, Gram-Schmidt method will give me the answer. Because when we are starting with a basis, that is linear independent set, I can transform this basis to a orthonormal basis. And that process is known as Gram-Schmidt method. That is an algorithm, that is a particularly algorithm, nothing else is there, which use the projection thing, the formula kind of. So this is how we should do that. You use the projection of that vector, take the minus of that, and do the calculation and get a new basis, which is an orthonormal basis. So whenever I have given a basis, I can generate an orthonormal basis by using Gram-Schmidt method. So till now, whenever we have said that let G be a vector space and consider an orthonormal basis of that, this Gram-Schmidt method is basically behind all of that. Because of Gram-Schmidt method, we can know that there exists an orthonormal basis and we can choose the orthonormal basis like that. It will always exist.
And sir, this method is the proof actually that a vector space can have orthonormal basis, right?
Exactly.
Okay.
So one more question out of curiosity. Whenever we are considering projections, we are just talking about subspaces, vector subspaces, right? We are not considering affine spaces, right?
No, subspaces. We are considering subspaces.
Does the concept really exist, or is it just out of scope, or it doesn't exist at all? It may exist, right?
It may exist. We can transform, first of all, if you remember how affine space was created, we can bring the affine space back to a subspace, right? And then take the vector and then take it back, the same thing. Okay,
simply find the projection on a subspace and then again translate it by the vector. Exactly. We get F-space.
Yeah, it is not actually very difficult, as you are saying. Just do the projection on the subspace, translate it to that. Okay, so I think today whatever we have discussed, we have done step by step and reached to some certain level. I hope it's clear.
So I'm gonna go through that PDF again. For last time. just to get another perspective, if we like, if like personally from my POV, if I have anything to ask or not.
Yeah, yes, sure.